Today we are going to talk about concavity, which is really describing the shape of the graph. So up until this point, right, we were talking about whether the graph is increasing or decreasing, and now we're going to actually talk about the shape of the graph that it can take on. So concavity will change, right? If something is increasing, it can look two different ways, which we're going to talk about in a second here. So first of all, we're going to talk about the test for concavity. So we're going to let f be differentiable on an open interval I. The graph of f is what we call concave up on I if f prime of x is increasing on the interval, and concave down on I if f prime is decreasing on the interval. So when I say f prime is increasing, the way that we found if f was increasing was to find the derivative and find out where the derivative was positive. So this time we want to know where f prime is increasing, so we take one more derivative and we do the exact same process. So the test for concavity is we find the second derivative, and essentially if f double prime of x is greater than 0 for all x in the interval, then f is concave up on the interval, and if f double prime is less than 0 for all x and I, then the graph of f is concave down. So let me just put this in perspective for a second. It seems like a lot of information, but when we were testing for increasing and decreasing and mins and max, basically we found the first derivative, set it equal to 0, and then we found any places where the first derivative didn't exist or it was undefined, or where it was equal to 0. I said the same thing twice there, sorry. And then we tested in the interval. This is the exact same test, only using the second derivative, and instead of increasing and decreasing, it tells us about concavity. Okay, so what in the world is concavity to begin with? Okay, so I can draw an increasing graph two different ways here. I can draw it like this, and I can draw it like this. Okay, both of these are rising from left to right, but this one here is what we say is concave up. You know, kind of like if you have an upward tilt to your hand. So this one is concave up, and this one is called concave down. So this helps us decide what the shape of the graph looks like, right? So these are increasing, both of them. So if I draw decreasing graphs, I can draw them two different ways too, right? So decreasing would be falling from left to right. So I can draw one that looks like this. It has kind of an upward tilt. I sort of think like it'll hold water. I know it really won't, but if you set something in there, it might hold it there for a second. This one picture is concave up. And then I can also draw it like this, right? This is concave down. So this helps us, concavity, helps us draw a more accurate picture of our graph again, right? It's the shape of the graph and how it's behaving, right? So the process, this is exactly the same process as we did the first derivative test for increasing and decreasing. It's just that we're going to use f double prime this time. So we find where f double prime is 0 or where f double prime doesn't exist, and then we test in between, just like before, okay, only using the second derivative test. All right, so we're going to find intervals of concavity. So first of all, I have to remember that intervals of concavity, what tells me about my concavity is my second derivative. So that's the first thing I need to find. So I need to find the first derivative on the way to the second. So I'm going to rewrite this. Since I have just a constant in the top, I'm going to use, I'm just going to pull this up with a negative exponent. So I'm going to write this as 6 times x squared plus 3 to the negative 1 power. So my f prime of x is, so it'll be negative 6, I'm using the chain rule here, 6 times negative 1 is negative 6 times x squared plus 3 to the negative 2, and then times the derivative of the inside, which is 2x. All right, so I'm going to rewrite f prime without this negative exponent. So these two things are on top, so I multiply them together and get negative 12x over x squared plus 3 squared. Now, we might not like the quotient rule that much, but when we're doing these and we know that we're going to try to find out where the next derivative is either 0 or undefined, then I really need to make this into a singular fraction. And the good thing about the quotient rule is I always end up with a singular fraction with just one denominator. So now I'm going to apply the quotient rule to find the second derivative. So my second derivative will be the bottom. So I have x squared plus 3 quantity squared times the derivative of the top, which is minus 12, then minus the reverse. So this will actually become plus times 12x because I have a minus minus, so I just changed my sign there. And now I need the chain rule for this piece. So that would be 2 times x squared plus 3 to the first power, which I'm not going to write since it's the first power, I'm subtracting, times the derivative of the inside, which is 2x, over x squared plus 3 quantity squared. Okay, lovely, right? Maybe not quite as lovely as I'd hoped. But, so this is a way that we can simplify. So I want to simplify this. Now, sometimes I just want to expand it and be finished. But I really don't want to go crazy because I notice here I have x squared and it's raised to a second power, so that would give me an x to the fourth term that I really don't want to deal with. So I want to set this equal to 0, so my goal would be to factor the top anyway. So this is a way that we can simplify. So we've not done a lot of this, so let me walk you through this. So what I see in common so this is one term, and here's another term, right? They're separated by this plus, so all of this multiplication is 1, all of this multiplication is the other term. What I notice is that they definitely have an x squared plus 3 in common. So I'm going to factor out x squared plus 3. This one has 2, this one has 1. We always go with the smaller, okay? Now this has a negative 12 here. So actually, and this also has a 12 here. So I'm going to factor out, actually I'll factor out the negative 12, okay? All right, so now that's all the things that they have in common, right? So now I'm going to open up I'm going to put a new bracket here. So I'm going to multiply this times something here that'll give me back this. So I already have the negative 12, and I already have one of those. So what I have left is just 1x squared plus 3. I can put parentheses around it, but I don't need to put parentheses around it, okay, because it's to the first power, so I don't really need them. All right, so now I'm going to factor out a negative 12. That's actually going to make this a negative here, right, because that'll take that away, because then this times this here should be positive, so I'm going to have a negative times a negative. So now I'm going to need, I've gotten this is done, I still need this, and I've got this. So I basically need this x times this 2 times this 2x. All over x squared plus 3 quantity. Oops, I didn't raise it to the fourth. Did I? Ooh. So this is to the fourth power. Sorry about that, right? Because I forgot to square the denominator again. Okay, so now I have f double prime of x is equal to, so I don't want to multiply these two things together, so I have negative 12, I'm just putting it in a different order, x squared plus 3. I'm going to clean up the inside here, so I have x squared plus 3, and then I can multiply all three of these things together and get minus 4x squared over this x squared plus 3 to the fourth. Now since I have this times this times this up here, I can simplify this. So I have one of these here, it's common with one of those here, so now I have 3 there. So my f double prime of x then is, I have the negative 12. Let me combine these. I have x squared minus 4x squared, so I have negative 3x squared plus 3 all over x squared plus 3 cubed. All right, so now it's all cleaned up. Now I'm ready to find my zeros. Okay, so I want to know where f double prime of x is equal to 0. Well, that will be where my numerator is equal to 0, because my first step would be to put 0 over here. I'm going to multiply both sides by this piece. It cancels on this side and it turns into 0 on the other. So this ends up being negative 12 times negative 3x squared plus 3 is equal to 0. Now the negative 12 can't be 0, so I can ignore that, or I can divide it away. So if I divide both sides by negative 12, then I'm just left with negative 3x squared plus 3 is equal to 0. I'm going to add the 3x squared, I like my leading coefficients to be positive, to the other side. I'm going to get x squared is 1. So that gives me x is plus and minus 1. Those are critical numbers. Now, to find out where f double prime, do I have any critical numbers from the denominator? So I would set the denominator, I get x squared plus 3 quantity cubed is equal to 0. This would be places where my f double prime is undefined. And if I take the cube root of both sides, I get x squared plus 3, and then I move it to the other side and I get x squared equals negative 3, and I can stop. Right? There's no solution here. So I just have these two critical numbers of my second derivative, which are 1 and negative 1. So just like I did before, I'm going to put these on the number line. Okay? So here's my negative 1, here's my 1. I'm going to test in between them, just like I did with the first derivative. It's just that I'm going to plug, when I'm testing in the second derivative. So this is my nice cleaned up derivative. Okay. Actually, let me write f double prime a different way, just to make it a little bit easier for us. So if I could factor out a negative 3 out of here, out of the top, so I'm going to rewrite this as negative 3 times x squared minus 1. Right, if I factor out the negative 3, and now I can multiply the negative 12 times the negative 3. So my cleaned up version could be 36 times x squared minus 1 over x squared plus 3 quantity squared. So this will make it a little bit, I won't have to deal with quite so many negative signs this way. But if I do everything correctly, I could still go back and test it here. So I'm going to test a thing in each one of these intervals again. So I'm going to rewrite this as negative infinity to negative 1. Negative 1 to 1. These are my three intervals, and 1 to positive infinity. All right, so I'm just going to test a point in each one. So I'll start with f double prime of, we'll just say negative 3. So I'm going to have 36, which is positive. I square the 3, and I'm going to get 9 minus 1, which is positive, so I get positive overall on top. And I get 9 plus 3 quantity squared, which is positive. So positive here. My interpretation of this, right, my second derivative is this is the place where it's up. Plus goes with concave up. All right, so let me choose f double prime of 0, which is in between here, right? If I plug in 0, then I'm going to get negative 1 here times 36, well that's negative, over 3 squared here, which is positive. So this will be negative in here. And in my second derivative, negative goes with concave down. So I get a negative value over a positive value. Okay, which is negative. This one's positive. And then one more, just something bigger than 1, I'll just do 5 to not be symmetric. So that'll be positive, right? That doesn't change. This will be positive because 25 minus 1 is positive, and then this will be positive, so it's positive overall. Okay, so my intervals of concavity, right? I am concave up in the positive parts. So I'm concave up between negative infinity and negative 1, and 1 to positive infinity. So this one and this one. And I just put this little u in between them to hook them together. Then it's concave down in the middle between negative 1 and 1. So those are my intervals of concavity. So usually the hardest part of doing this is finding the second derivative and cleaning it up. Okay, so that's our first example. So when we were doing our first derivative test, right, when our derivative changed sign, right, depending on which order it was, if it was continuous there, then we found out that it was a minimum or a maximum point. When my second derivative changes sign from concave up to concave down, we call that a point of inflection. Okay, so a point of inflection is a point on the graph in which the concavity changes. So when I'm looking at my second derivative and assuming that it's continuous there, then any place that my second derivative changes sign, is a point of inflection, and I don't even have to worry about which direction. It goes from positive to negative, it goes from negative to positive, it's a point of inflection. So I have this picture here. Now points of inflection, right, they occur where either f double prime of c is equal to 0 or where f double prime of c fails to exist. So this is just the same idea as where the min and the max occur, except for in the first derivative. So, right, it's easy to see, like, this is the local min, this is the local max. Points, and this would also be a local min, just FYI. Right, those are relatively simple to pick out in the graph. Points of inflection are not, they're a little bit more subtle to pick out. So here, so I'm thinking shape, right, concave up is like my hand is tilted either up, right, like this, or I can't turn it the other way, but so, or it's kind of got the downward curve to it. Somewhere about right here, I would say, is a point of inflection, because here my graph is sort of down, right? It's got that curve to it, but up here it's got this curve to it. So somewhere around here would be a point of inflection. This is what they look like. Okay, and then also somewhere about, where's a good, actually probably right around here is a point of inflection as well, because this has like this downward tilt to it. Actually, maybe it's more up here. And now this one has this upward tilt to it. So it goes from down here to more up here. See the difference in the curve? Okay. So points of inflection aren't quite as obvious, right? Obviously, this one is the local max and this one is the local min. My points of inflection are a little bit more subtle and maybe not quite as easy to locate exactly. But it's somewhere in this vicinity. It's probably more here than there. Okay? So that's what a point of inflection looks like. And again, it's just a place where, assuming that my function is actually continuous there, it's a place where my second derivative changes signs. And if it's going to change signs, it's going to happen at a place where the second derivative is equal to 0 or the second derivative fails to exist. So it's just taking our intervals of concavity one more step. Okay, so for instance, on that problem that we just did here, right, that was this problem where we finished off. And if I look at my original f, right, there's no domain restriction on this, because if I look at the denominator here, I can't make x squared plus 3 equals 0. So my domain here is all real numbers. So that means that here, right, and here, where I went from positive to negative, concave up to concave down, and concave down to concave up, that at x equals 1 and at x equals positive 1, I'm going to find points of inflection. Okay? Those would be called points of inflection. And I would find them, the other point, by plugging them into f. Right? When it's a point on the graph, I take it back originally and then take, so my at double prime gives me at what x value I'm going to have the point of inflection, and then I plug it back into regular f to find it. Okay? So this would give me a point of inflection, and also the point 1, f of 1, would also be a point of inflection. Actually, those are pretty easy, so let me just pop them in here. If I plug in -1 here, f of -1 is 6 over 4, and actually f of positive 1 will be the same, right? Because, so in both cases I get 3/2. So when I look at the graph, at the point -1, 3/2, I should see that my concavity is changing there, and at 1 and 3/2 as well. All right, so let's go through that process. Oops, there's the other problem. So let's do an example. So I went back to a polynomial because those are really nice to do multiple derivatives on. Okay, so just to put it in perspective, right? If I ask you to do this, right, it's not going to be terribly algebraically complex, because I don't want you to spend your whole time doing an example. Now, problems for homework, those are fair game for cleaning up. But don't panic that you'll have to spend 10 minutes doing algebra on the exam, okay? So if I'm going to find intervals of concavity, then I basically need to find f double prime. So I need f prime on the way there. F prime would be 4x cubed minus 12x squared. That seems so simple after the last one, right? And now I need f double prime, which is 12x squared minus 24x. So I want to know where this is either 0 or undefined. It doesn't have a denominator, so it's not going to have an undefined place. So I'm going to set it equal to 0. Again, factoring is my friend. I have a greatest common factor here of 12x, leaving me with x minus 2. So I'm going to get zeros at x equals 0 and x equals 2. There's my 0, there's my 2. I'm going to test back in my second derivative, right? So this is the one I'm dealing with. I just needed to find f prime on my way to f double prime. So f double prime of negative 2, for instance, would be, okay, this will be, let me put it in here. It's a little easier with the multiplication. If I plug it in here, it'll be negative. And if I plug it in here, it will also be negative. So I end up with a positive in there. So it's concave up there. And this is a polynomial. It's continuous everywhere. So if I change sign, then it will be a point of inflection. My point is, if this had something in the denominator that would cause a vertical asymptote, then even if it changed concavity there, it still wouldn't be a point of inflection because I can't put it on my graph. Okay, so then I'll try f double prime of 1 is a nice integer between 0 and 2. If that's true, then this will be positive. 12 times 1 is positive. 12, or actually 1 minus 2 is negative, so I end up with negative overall. Right, so then it's concave down between 0 and 2. We're going to put all of this together. We're just doing the algebra right now, but we're going to graph these very specifically, and we'll put it sort of all the pieces of the puzzle together in a future lecture. So now I just need something bigger than 2, f double prime of 3, for instance. That will be positive, that will be positive, and so I'll get a positive value overall. Right, so my intervals of concavity, right, I would say this is negative infinity to 0, this is 0 to 2, and this is 2 to positive infinity. And so these two intervals are concave up. This one in the middle is concave down. I could write that out formally. But this time I was just wanting, oh, actually no, it did say find intervals of concavity. So let's write that. Concave up in the intervals from negative infinity to 0 and from 2 to positive infinity. You can write these as inequalities as well, but I think this is actually easier to just use interval notation if you feel comfortable with it. And so then concave down would be this part in the middle. So I'm changing concavity here and here. So that means that at 0, f of 0, and at 2, f of 2, these are both points of inflection. Okay, so now I just want to, my last part is to not leave this f of 0 and f of 2 here. So my double prime tells me at what x value it will happen. My y coordinate comes from the original function, right? So I'm going to plug in, so f of 0 here would give me 0 back out. So at 0, 0, right, these are points of inflection. I'm actually giving the point value here. And then if I plug in 2, right, that's my other one, so I'm going to have 2 comma. If I plug in 2 here, then I get 16, because 2 to the 4th is 16, minus 4 times 8, because 2 cubed is 8. So I get 16 minus 32, so my y-coordinate here is negative 16. So my 2 points of inflection are at 0, 0, and 2, negative 16. I encourage you to kind of graph this, right? Look on Desmos, go graph this and see what you see at these points. Hopefully you can kind of interpret the concavity there. So we'll just do one more concavity example, and since we're using trig, just for ease, I know we got kind of bogged down in some of those min and maxes, so we'll just kind of cut the interval from 0 to 2 pi just to make it a little bit easier. So we're just going to talk about intervals of a concavity and points of inflection just between 0 and 2 pi. Okay, so since I'm dealing with concavity and points of inflection, I know I need to do the second derivative. So the first would be 1 and then minus 2 sine of x, because the derivative of cosine is negative. So that's f prime. F double prime of x, then the 1 becomes 0, and I get minus
to cosine of x. Okay, so now I need to know when this is equal to 0. So 0 equals -2 cosine of x. I can divide away the -2, and basically I'm just looking for cosine of x is equal to 0. Now I know that cosine of x is basically at the very top and the bottom, it's equal to 0 of the unit circle, so that would be at pi over 2 and 3 pi over 2. Okay, so those are our numbers. We're going to put on our number line. Remember, this is my second derivative. So, you know, if later on when we start combining the first and second derivative, it's always kind of a good idea to sort of label them. I'll say, this is my second derivative. Okay, so I know I'm going to end here at 0 and 2 pi. All right, so if I consider my f double prime, so here is my first 0 of my second derivative, and here's my second one, right, in this interval. And so from 0 to pi over 2. So from 0 to pi over 2, like here's my second derivative, so I want to say, is that positive or negative? Well, I know from 0 to pi over 2 on the unit circle, my cosine is always positive. So if I have a positive value times this -2, it's going to be negative in here. So that means I'm going to have basically a concave down picture, right? So then between pi over 2 and 3 pi over 2, pi is a nice number to check, right? So when I plug in pi, then pi gives me -1 for my cosine value, so then I have -2 times -1, which means it's positive in here. You can put 1 plus or 1 minus, I mean, it doesn't matter whichever way you like to do it. And then 3 pi over 2 to 2 pi, that is the fourth quadrant, and cosine is positive in the fourth quadrant. So basically I'm going to have a positive number times a negative number, which is a negative number. So my intervals of concavity, I would say it is concave down. And I'm just going to use it's from 0 to pi over 2 and 3 pi over 2 to 2 pi, right? Because that's where it's negative. So these are my down spots. This is my up, right? So, oops, sorry. All right, and so then I also have a concave up spot in the middle there from pi over 2 to 3 pi over 2. And since I know that this is a continuous function, and if you don't believe me, you can go graph it, then I know that both of these x values are going to give me points of inflection. So I know I'm going to have points of inflection at x equals pi over 2, because it changed concavity here, and it also does again at 3 pi over 2, and if I was going to do the whole number line, we'd be changing concavity forever. So that's why I just cut it off here, just to make it a little bit easier for us. And so then my last step is just to find my points of inflection, like if I was going to put them on my graph. That's an important thing for me to remember. And so let me just rewrite f down here again. So I go back to regular f here. Right? Whenever I'm testing these, I can't say it again, whenever I'm doing the first derivative test, right, or I'm checking for concavity, I'm always putting these back in the derivative to check if it's positive or negative. But when I go to find the y coordinate to actually graph it, then that's when I go back to f. So I come back to original f, which is x plus 2 cosine of x, and let me do f of pi over 2 so I can find the other coordinate here. That would be pi over 2, and then plus 2 times the cosine of pi over 2, and cosine of pi over 2 is 0, so I just end up with pi over 2. So I end up with pi over 2 is a point of inflection, and I can do the same thing with f of 3 pi over 2, and that gives me 3 pi over 2 plus 2 times the cosine of 3 pi over 2. Again, I don't know why I put, the cosine of 3 pi over 2 is 0, so I end up with 3 pi over 2 again. So basically I have 3 pi over 2, 3 pi over 2, and pi over 2 are my points of inflection. All right,